Okay, without further delay, we are going to move forward with our second keynote speaker. He is one of my good friends, and we are looking to meet each other from long time. So, Alhamdulillah, we meet after 9 or 10 years through this platform. So, Prof. Abou El-Kacem Qaiss is currently working as a director of the Composite Nanocomposite Center at Moroccan Foundation for Advanced Science, Innovations and Research, Institute of Nanomaterial and Nanotechnology in Rabat, Morocco. His research area include the hybrid reinforced, filled polymer composite, advanced material, graphene nanoclay, lignocellulosic reinforced polymer composite and modifications and treatment of the lignocellulosic fibers. And also is working on the polymer blends, and he have a good teams because I continuously watch him. He is working a lot of works on the dome fibers, one another form of the palm. So he have a lot of works, and also he works some on the date palm fibers. And we also together edited some book together through the Springer on the topic of nanoclay and all these things. So without further delay, I call the Prof. Qaiss to please come and give the talk on recent advance on the bio-thermoplastic based date palm fibers. Please come on the stage.
Assalamu alaikum wa rahmatullahi ta'ala wa barakatuh. Thank you very much for organizing committee to invite me for this prestigious conference and to give me the opportunity to meet my brother, Professor Jawid. We work and we collaborate more than 10 years, and it's the first time we meet. Thank you very much for the new technology that give us this opportunity. Sincerely, after the conference of Professor Morsley, I have the question as a researcher, and we are the duty to ask, how can we update and increase the quality of the several applications in our history to use that palm fiber? I think that's the approach. We must ask this question. How can we improve the quality and improve the industrialization of some product that is made manually? We focus now of the new approach, the use of chemical approach to extract some the high value of products from natural fibers in general, especially on the date palm fiber. I will talk about the recent advances of the recent thing of the manner to have our research in the natural fibers or the work on that palm fiber in the market as high value. In my laboratory, I have several work on natural fiber and that palm fiber to extract, for example, the cellulose microfibril, cellulose nanocrystals, and cellulose monoliths. These, especially these, can have several applications in some treatments because it offers a lot of surface, for example, for wastewater treatment to extract some specific waste products, waste components in the water, and also the cellulose hydrogel. And as application, the manufacture of film as 100% of cellulose. That is, at laboratory scale, we can use from a solution as viscose product to produce a film, but it need, at nowadays it is used at laboratory scale by evaporation of solvents. In this case, we use the water to obtain a transparent film. It's like a plastic film, the same transparency. But the production at industrial scale is under study. And for this, our dream as a researcher and the dream of our researcher is the industrialization of this approach. In our main, we have the extruder. In this extruder, we have three parts: the feeding of the materials, the transformation states of the materials. Here in the extruder, we use a thermal effect of temperature to change the state of the material. And we have the cannon drain, or the compounding to obtain the composites or the granular composites between matrix and reinforcements. That is our dream. One day, we use in the feeding the cellulose, and we obtain a film to industrially, for the application as the industrials. Here we have the definition. To have this or to apply this, the material must have a thermoplastic behavior. What is the thermoplastic behavior? Is we have the materials, and under temperature, we change the state. That is usual. We talk about, for example, PP or polypropylene or polyethylene. And we have several properties that is similar to what we obtained when we produce the film from cellulose. We have the transparency, we have the acceptable mechanical properties, and we have the barrier, the barrier properties, especially when we use it in the packaging. To reach these, I will talk about two approaches. The molten approach, as we see, we have, for example, for thermoplastic or for semi-crystalline polymer, we have the thermal properties. These thermal properties when we have the displacement between the chain. Under temperature, it facilitates these. And we have the degradation, the onset degradation of the materials, and the process into temperature is chosen between the two temperatures. And we chose the temperature higher than thermal molten temperature to reduce the viscosity. That's the approach when we use the standard thermoplastic. In the case of the cellulose, we have the same shape. We have the linear chain, and we have the intermolecular hydrogen bond. It's the weak bond. And under temperature, the problem, under temperature, we have the degradation of the bond inside the linear chain before the displacement intermolecular. We can ask this. The intermolecular chain is weak than the bond inside the linear. But we have the 3D cross-linked of the chain. It's the difficult. We have the density of the hydrogen bond is very higher than the density of the bond inside the chain. It's for that we have the degradation. The onset degradation is before the displacement of the chain, of the linear chain. In this, we cannot use the molten approach because the material is degraded. In this, in several work, we try to use the natural fiber as reinforcement in thermoplastic composites using the standard industrial techniques like extrusion or injection molding, and we can reach more than 20% of natural fibers to produce a composite by extrusion. But the problem, we still say the change of the color, and we don't talk enough of that. That is mean we have the degradation of the natural fibers. We can improve the adhesion at the interface, but different techniques, but different functionalization, but the development of a new molecule to bridge between the matrix and the reinforcement, but we still have the degradation and the change of the color of the material. And the color is decay in the industry, because we must have the neutrality of the color to add a master batch of the color and to produce the part of a specific color. In the case of use of natural fiber, we still have the brown color. It seems that we have the degradation of the materials. And the second approach is the cross-linking. The cross-linking, when we produce the bead from hydrogel, we have the cross-linking media, and we have the bead before cross-linking. The size is depend on the tension of the surface and the configuration of the system. And we can obtain the cross-linked bead, which can be used also for different treatments, because we have the ultra porous materials. This is the same used, for example, here for the ketosane and the black carbon for specific uses, and obtained the bead, and this bead can be used to for absorption for specific components. For example, we use it for extraction of the cadmium from phosphate. As you know, Morocco is the first exporter for the phosphate, and the Moroccan phosphate, we have more than 60 ppm in cadmium, and we must extract it. Here we have a process which is used in textile to obtain the rayon from cellulose. And we have the same batch for the treatment of the cross-linking of the material. We will use the same approach with the feeding with the viscose solution. And we ask, how can we produce the viscose solution from our products or from the natural fibers? Different steps of treatment we will follow. Our raw materials in this is our objective, to obtain the viscose materials, which can be feed the process to obtain a cross-linked in continuous production for the cellulose. Our raw materials in this case is the pulp of cellulose. Is used, for example, it is presented yesterday to produce the paper. This is the microfiber with specific length, and we use this for the first step is called steeping. We saturate the material with sodium hydroxide, and before obtain the pulp of paper, we use the sodium hydroxide to extract the lignin. And now we use it to saturate the material and to obtain the as gel configuration or structure of materials as viscose materials. It's called soda cellulose. After that, we use carbon disulfide to open the link and to have a more functional group to be treated and to cross-link it during when we have the contact in the cross-linking media. And we obtain soda cellulose or sodium cellulose xanthate. And the last step is the mixing. We have we use a small quantity of sodium hydroxide to have a more homogeneity of the solution and to have what we called a solution with the stable state. And we cannot have a decontamination of the materials. And we obtained the viscose materials. These viscose materials, which we must have a specific properties, especially rheological properties, because we will use it in the extruder or a process similar to extruder, like what we use, for example, of polymer. When we use and we talk about the grade of polymer, it's for extruder or extrusion or for injection molding. These depend on the length of the molecule, and we do some characterization. Rheological, for example, plate at melting state, or we use the MFA, melt flow index. It gives us properties how the materials must flow under a specific day. For rheological, for us, we have different kind of rheological behavior, but the main character that our viscose must respond is thixotropic nature. This thixotropic nature, it means that the material have different viscosity depending on the shear rate. And at high shear rate, we have a low viscosity, and at shear rate, small shear rate, we have a high viscosity. These allow us to have a right or the flow of the materials with the high viscosity, and we have enough time to treat the material inside the cross-linking solution. That is the horizontal extruder. But in our case, it is difficult to use this process, and we can use a vertical flow of the materials. This is a schematic of how can the process will be designed out and can be worked. This continuous process, we have the quantity of the materials and the pushes throughout a day. This in flat day to have a film, and we have a regenerating media of cellulose. And also we can use a system as extruder. And we have the screw and the material flow today, and we can have a continuous flow of the material and continuous process. Now I will talk about the generating media in this process. Here in our laboratory, we work on the transformation of this injection molding machine, which is vertical, and it is with a low pressure, because here we have a screw as extruder transport the materials throughout the day. And for regenerating batch or regeneration media, we have a specific time of the treatment. Is for that the material have this path, and after that we have the material. We need just washing and drying the material to obtain a film of cellulose. And this, we use sulfuric acid. We have sodium cellulose xanthate in the in, and the out we have materials, our cellulose, and after washing we have just a film of cellulose. And I will talk about the main point is the viscosity and the rheological behavior of the material. This is the process which is used actually to produce a thin rayon of from cellulose. Exactly, we have the same approach to obtain the viscous solution. And the difference, and in the case of the rayon, we have more specific surface of the treatment, and the time of the treatment is very short. In the case of the film, we must have a thin film, and the duration of the treatment is very large. And other use of the viscous materials, as I say, is the extrusion, and we can, for the coating, use the spin coater to deposit a surface of coating of some functional application in the surface, and or the use of the fiber, and after that we can use the fabrics to produce some specific part. And this approach is very used in the textile industry. And our challenge is to control the properties of the film. We can produce the film, but for application, we must respond to the specific properties. Here, I will talk about the ductility of the materials. It's the capability of the material to deform plastically before finer. And we need this for application. When we talk about a film of cellulose, the first application is the packaging. And the packaging, we need some plastic deformation or thermoforming of the materials. And to control the rigidity, I will talk about this. And also for the process, we must have a specific rheological properties, especially the control of thixotropic of the materials. And for the rigidity, we can talk about the nanocomposites and use different nanoparticles to reinforce the matrix. And for this, we have in our laboratory, we work on the synthesis of different nanoparticles, cellulose nano crystals, graphene nanosheets for graphene, and different states to obtain graphene and its derivatives, carbon nanotube, carbon nanofibers, metal oxide. These we need it for specific application. For example, when we want to talk about the electrical conductivity of the film, we need to introduce some specific particle like metal oxide nanoparticles, which can be used at the small quantity, and we can respond to the specific application. Also, the use of clay nanoparticles, and in Morocco, it's rich on the Bantonet on the north of the of the Morocco. Is for that our first project is to valorize in my team to valorize the Morocco research. We worked on the different kind of nanoparticles and the bentonite from the north of the Morocco to produce the nanoparticles. And here we can produce the materials, and we as a researcher, and we must respond to the specific application. Can we predict the behavior of the material before formulation? But it is sure when I mix two components, I will obtain the third one. But can I predict the behavior of the result of the mixture of products? And for that, it is very important to work on the modeling of the materials and to use the theoretical background, because we work on the applied researcher, and we have the boundary for the fundamentals and the applied, and we must use some fundamentals to produce materials with specific properties to control, for example, mechanical, thermal properties, rheological, and study, for example, in the process when we talk about the fiber, the orientation of the fiber along processing of the materials. And when we talk about the modeling, especially in the mechanics, we base our modeling on mechanics of materials, which is based on two assumptions: the continuity of the matter and the continuity of the transformation. It means that when I take a volume at micro scale of the material, it is sure that inside this volume we have the material. All components that describe the materials. And when we talk about the continuity of the transformation, this is continuity of the materials, and this continuity of the transformations, it means that if we have 2 points, closed 2 points, after transformation or after deformation, we still have the 2 points closed, and they deform. In this, I can talk of the matrix that describe the transformation of the materials. Donc we need on the continuum of mechanics to have or to validate the two assumptions. That is a different formula. And here, in our case, in the modeling, we can model at micro scale, and when we switch to macro scale, we use some formalism, and the properties of particles is different of the micro scale of the materials is composed by different particles. And the question: can we use this approach or homogenization approach based on continuum of mechanics to model the materials at nanoscale? As I say, at nanoscale, we must to model from nanoscale to microscale. I will take the elementary representative volume. And at nanoscale, when I take this volume at the nanoscale, probably inside there is no materials. And the first assumption, the continuity of the materials, is not validated. And the transformation, we talk about the transformation in continuous mechanic and infinitesimal displacement. This is at the nanoscale. And the case of nanocomposites or nanoparticles, we can have this deformation at nanoscale in the scale of the infinitesimal, and the second assumption is not validated. And we can see that all formalism from continuous mechanics cannot be used. And in this, we need the collaboration on physicians and chemists, because we need the modeling and the describe of the materials at atomic scale, at the nanoscale, and we must model the link. It's for that, for example, when we talk about the composites of the materials, we talk about the reinforcement and the matrix, and we cannot take the interface as the third phase and take it as phase in our model. And for the modeling, we can follow some point. For example, a spectral ratio that we talk about the nano particles, it's very difficult. And we must model this or use the high, for example, atomic force microscopy or the TEM to obtain the characterization of the material to input and to determine the aspect ratio. Fiber aspect ratio, when we talk about aspect ratio, it's the shape, and here we talk about the shape and the length and the diameter of the fiber. And we take the interface. The advantages when we take, for example, the viscose reinforced with the cellulose nanocrystal, we didn't have the problem of the compatibility. We have the same functional group in the matrix and in the reinforcement. And we must talk about the good dispersion and distribution. Both we have the adhesion at the interface, that's the first parameter, and the second parameter is the design of the processing of the equipment, how can be dispersed and distributed the nanoparticle inside the matrix. In the future, it's sure that at the engineering scale, we must design the process responding to different states, and we must work on how can we use the film as in thermoforming. We cannot use the temperature, what is the equivalent, and can we give us the same result, and how can we use, and can we recycle these materials, and can we see the result? The cellulose can be like a pulp of the paper and introduce it. It's sure it's not the same, but can be as the first step to recycle the materials. Thank you very much.
Thank you, Prof. Qaiss, for taking totally technical side, for more research on that one, fundamental research, and towards how it can be fabricate different types of product and characterizations and all these things. So now we open the floor for the Q&A. So please, if anybody have questions, please. Is the student want to ask the questions? Okay, with supervisor, okay.
Actually, Professor Qaiss, I'm his grandson, because he taught his son, and then I'm his grandson.
Okay, so you are his student and then
yeah.
grandson, okay.
Yeah. So I just want to challenge my grandfather for a simple question, because if we look carefully, us like in the Morocco region, I mean the whole MENA region, Middle East and North Africa, we have tight competition if we compare ourselves with Europe, because they have forests there. So they have unlimited supply. So to balance this with date palm, or let's say doom, how can we balance, or how can we compete with them when we don't have enough supply?
Thank you very much, Brother Salim. Is the the student to my students. I am agree with you. The competitive in we use, for example, in Morocco, we talk about the alpha fiber, dome fiber, date palm fiber, but the concurrence and it cannot assume. But it's for that we talk about the high value of the materials. We can talk, for example, to produce the paper. We didn't have more wood to the balance between wood and the fiber, but for the high value product and to extract the high value component from the natural fibers, I think that it's based on the knowledge. As in these, we can have the balance.
Okay, Prof. Qaiss, thank you so much. Any other questions? The Prof. Home is one to ask question.
Hello, Professor Qaiss. Thank you so much. I'm Home Dakar, University of Portsmouth, UK. You really captured theoretical aspect, experimental aspect, as well as modeling aspect in your presentation from nano to macro. Have you received any results from your experimentation, and can they be related to particular applications?
Thank you very much for your question. Yeah, we have some results, but it's still at the laboratory scale. And we work on the unit operation to validate unit operation in the process. But we have some results, and it is competitive, and we can have the application. And also, we characterize our materials to respond to the specific application, especially for the packaging. How can we enlarge the life of, for example, the feed inside our functional packaging?
Right. Yeah, just to elaborating on that, we are also working on packaging material using dead palm fibers, using dry blending and melt blending and comparing their properties. And some of that result I'll be sharing later in the presentation. I think achieving the challenge, the permeability, water vapor permeability, oxygen permeability is a big challenge. I'm sure you are facing that as well.
Thank you very much. Yeah, when we use, for example, I talked about the Moroccan clay, the bentonite, which can be transformed on the monomer unit at the nano scale. It is useful for to improve the barrier properties of the materials, and we work on this. It is very difficult to disperse and distribute the nanoparticles inside the matrix, but it can be used for this. Thank you.
Okay, please give the mic to him. Okay. We have time. Don't worry that we have time, so we will take more questions.
Thank you, Prof. I'm just commenting on your grandson question. It is not a matter of competition between West or East. Your work is about scientific discovery and scientific research. So it is a growth to the international community. The method and discoveries presented in your work, and the scarce of the material or the limited of the raw material, it is not the issue here, because I'm thinking you are working in a approach of research and scientific work that to use the local material and develop it into bio-thermoplastic, which is a useful material. And the value in this the value of the product is what is meant here, is not rather than the volume of the raw material available or not. Thank you.
Just give the backside. There's a lady. I want to ask a question.
Thank you very much. Professor Zahia Kabouche from Algeria. Congratulations for your nice presentation. Really, it was very rich. I would like to know if you have, for example, paper which is not so thick and you want to improve its thickness. For example, in chemistry, you have to use chromatographic paper like Wattman paper, number 3, or just for filtration, for example, number 1. What are the ingredients that you have to add to improve the quality of the paper, especially in the thickness?
In the,
Yeah.
when we talk about the paper, we have first the grammage of the materials. For example, this paper, we have 80 gram by square meter. But in these, we can work on the thickness. At the laboratory scale, paper making, we have the void. We must increase the void to have more compact materials.
That's right.
Yeah.
Yeah.
That this in the process and for the formulation, for example, we can use the calcium carbonate, which is usually used in the formulation of the materials and can enlarge the thickness.
Okay. Thank you.
You are welcome.
Okay, there's just pass the mic to him, that just next to you.
Dr. Salah Al-Eid from King Faisal University. Thank you very much for the deeply scientific presentation. The value-added products is really fascinating. I have 2 points. The first one is, what is the behavior of the products, the thermodynamic and rheological behavior when we recycle such films or beads? Are they going to follow the same melting points, glass transition points, and so on? This is the first question, because those properties are very important if the products will not collapse or need further costly treatments. This is the first point. The second point is, how long such products to be I think it's biodegradable. What's the length of the time also? And you added silver to the treatments and NaOH. What's the environmental impacts? How much you add? I don't know actually, but this is also a point of concern. And the third one is the economical feasibility of such a process. Thank you very much.
Okay, a lot of questions.
Yeah. Thank you very much. For the first question, it's sure. After recycling, we have the viscosity decrease. That is sure, because with the different, we start by the mechanical grinding of the material to be recycled before the solution of the materials. That's the rheological behavior must be controlled, and we must be added some component to increase the rheological behavior of the materials. The second question.
The second question is about how long the time for them to be biodegradable.
Sincerely, we didn't conduct this study, but the natural, 100% natural product in the nature. When I talk about the added for some synthesized particle, this corresponds to the specific properties. But when we talk about the packaging, we must be careful. We use the viscose reinforced with cellulose nanocrystals.
And just I want to add him that on the biodegradability, there is a different test as per the country, you know. So like, for example, if you go in Europe, EN 13432 or something like that. So that one, within the 6 months, the product can be decomposed in the soil, and the soil quality did not spoil with your materials, you know, like that. Germany have another, so different countries have another. So if you want to do, you have to follow up lot, you know, means that one. So it's a very big area of discussion and the research on that one. So I think with the limited time,
Just for the, when we talk about the film or biofilm for the packaging, it is not, it cannot be used as the, what we see as plastic. It's the specific application. Now we talk about the bio feed. That is, the packaging also must be bio. It's for that we use for the challenge. We cannot compare between thermoplastic film and film from cellulose, for example, for cellulose.
Okay, the Prof. Qaiss, thank you. So we have big applause for the Prof. Qaiss, and just catch the bit. And now I want to call the Prof. Ali Hassan Al-Marzuki from United Arab Emirates University to come on the stage to give the token of appreciation to Prof. Qaiss. Okay, Prof. Ali Hassan, thank you for that one, and thank you, Prof. Qaiss, for giving a good. So now we are moving forward to